Hey, well, welcome back. I tell you, I wonder how this will come out. We had a little glitch with the power. We have a bit of a challenge here today. One thing that I didn't get a chance to tell you is the pipes broke upstairs and we're flooded, and we've got all kinds of things going on. So they're turning water on and off, and I'm hoping we can still get this all done and to you in a timely manner, especially given this last week. But right there, we just had the power go out and the failure with the camera. But we're back up and running, and so let's pick up where we left off. And like I said, well, we're going to do everything we can to get this to you. Hopefully it won't be too late, but we want to get this in the lab to you because this is our final wrap-up week, and we just got some challenges with our building under all kinds of maintenance right now. All right, so here's what I was trying to do when the power went out, was to show you then that this will be my object, this ping pong ball. And if I put this right in front of the hemisphere, and I think it works a little bit better if I just kind of swing it back and forth. Or maybe even in a circle. Should I do a little circle? Can you see that, Ron? Okay. Yeah. I'm hoping you can see the image as well as the object. But I like this one because this one really does help show that the location of the image is actually in front of the mirror. And particularly when the ping pong ball swings this way, back in here. Because when the ping pong ball is right about there, and it goes back, it is like scenario number 2 over here, where the object is closer than the center of curvature. And so the image is further out, in this case, closer to you in the camera. And so hopefully when the object goes in, the image looks like it comes out. And the other way around, when the object comes out, the image goes in. Because right here is the center of curvature where I hang it straight down. And so I'm kind of crossing that barrier of going, when it swings out, further than the center of curvature, and when it swings in, go less than the center of curvature. And so that's this whole idea. And in fact, now that you might have seen this for a while, can you also see the change in the magnification of it? See, when it swings out, I'm hoping it looks a little bigger than the ping pong ball. And I should say image. Ron's looking at me. When the object goes in, but when the image comes out. So when the image swings outward, does it look bigger? And when the image goes inward, which means the object goes outward, does it look smaller? And hopefully it does. And there's one more thing that's a little hard to tell, but does it look upside down? And see, it's a ping pong ball, so it's hard to tell upside down. But that's why I put then some markings on here. And the markings probably could be a little bit lower, but the markings, the black markings, are a little bit below the equator. And so on the image, if I turn it around so you can see them on the image, see how they're a little bit above the equator. And so there is an inversion to it. And that's the fun idea of all of this. In fact, it kind of reminds me of, you know, where or why would you use this? And one of the first responses I usually think of in my mind is this one here, this making it bigger. If you've ever been to the dentist and he's got that round little mirror, and so I can see around in your teeth, kind of shoves it in there and looks around and examines your teeth. And at first look, it looks just like a flat mirror. But I know when my dentist leaves, I like to examine all the equipment, and so he's gone, and I'm like checking it out. And that mirror, if you look closely, you hold it up, you'll see a little dip in it, and you can even look at your own eye in it, and you'll see a magnification effect. And you can see that it is magnified. And so it's got that little dip. And so the mirror helps the dentist see, because not only does it get that angle right and uses the reflection of the mirror, but it also does have a magnification effect. And so both of those are really, really nice features that add to it. Where else? I guess telescopes are built this way. Oh, you know, a really good one that it's not so obvious. But this scenario here, hopefully what came across to you is that the image is in front of the mirror, and that kind of gives it a ghostly feeling. It really kind of makes it look like the light is coming from the center of the room. Some people even mistakenly call this a hologram. That's not what a hologram is. Hologram is something totally different, and we can talk about that at another time. But the light comes from the center of the room. That is, if I put the ping pong ball, say, right here, the light gets redirected, and it appears to be coming from right here. And so you're looking at this going, hey, there is the object. And I say that because one of the fun rides I like to do is the Haunted Mansion on Disneyland. And there's this one scene where you're in those little carts, and you're overlooking a dining room. And so you go up on these carts, and you're riding across, and you're looking in there, and you see all these ghosts dancing around. And the designers at Disneyland, the engineers, or what do they call them, Imagineers, they're real creative with using this. And what they did, and the whole reason you're up above them, is because underneath they've got little smaller curvatures of what you're about to see. And so they've carved them, and they've mounted them upside down. And so they're spinning around upside down, because what they do then is they reflect it off of this concave mirror. And so you're looking at the reflection. So the light comes off, and they've made it so that it bends the light, and they converge, and they make a real image right in the center of this dining room. So they're bigger and upside down. Of course, they look right side up to you because they've made them upside down. And they're bigger because they made up small, and so they can look human size, and so it looks like they're dancing, and they look very ghostly. They look like what we would call a real image. And I think we as humans are so used to virtual images. We are so used to seeing our image in the backside of the mirror that to see it out in front of us, to see it in front of the mirror, just is different. It's really ghostly looking. And so that's kind of the other example that comes to my mind. Maybe I'll do one more and we better move on, but it's kind of this in reverse, because what would happen if you were to put a light bulb right at the focal point here? And if you put it right here at that focal point, it would go off. And I think we mentioned this when we were drawing this on Wednesday, that it would come off and then kind of go straight out. And so it's kind of in this transition zone between this equation and this equation. And so you can kind of see it where here, as this gets closer and closer and closer and closer, this gets bigger and bigger and bigger and bigger, and eventually just kind of gets a big blurry mess. And so when the light bulb is right at the focal point, the light is just coming straight. See, because here it's diverging from the mirror, here it's converging, and so right here at this transition, it's kind of parallel. So that's a nice way to make the light from a light bulb go straight, even though by nature's sense it spread out. Well, I better move on because we have one more scenario here to talk about here, and that is for the mirror that's curved the other way. And so if I take a mirror, and I'll just turn this one around, or I also have another big one like that. What if I take a mirror that looks like this? And so here's this mirror where it hits here and it spreads out. I don't know if you can tell enough curvature on it, but this one is bowed outward towards you. So this is a convex shape. So I'm going to use the word convex here. And to start off, I'm going to show you then a convex. So let me take this concave one and put it away. Let me kind of clear off the board right here. And let me just show you, and I'll begin by pointing out that if I hold this in my hand, you'll see that, hold it sideways, here's the convex part of it. Here's the shiny part, here's the mirror part. Here's the magnet that I'm going to put on the whiteboard here. And so if I power down the chalk room lights and I put it here, you'll see that it does pretty much what I would call the reverse of what we saw for the concave. The concave, what I call the fun mirror, made the light converge. This is going to make the light diverge. In fact, it diverges so much that I think it's kind of hard to see, but it looks like it's going out this way, out this way, out this way, out this way, and out that way. And if I just remove the mirror, I'm hoping you can see that there is a magical point again. Now, it's not really where the light was focused from. And so sometimes we like to call this a virtual focal point, and the other one a real focal point. But, get some light back here. I'm hoping, and I'll just draw a line where the mirror was, you can see that that focal point is now behind the mirror. And if you let me kind of draw over here, and sadly I'm going to have to get rid of one of my cases of my fun mirror, but fortunately that equation is the same as the equation over there, because this too is going to be a question about, okay, if I put an object in front of it, where is the image and how big is the image? And you'll see that is another set of equations. And so there's a total of 3 different sets of equations, even though there's 4 scenarios. And so I want to get all 3 of them on the board at the same time. So if I erase this one, that equation is okay to erase, because as I said, it would be really the same equations of this one. But if I were then to say, here is your object, and now here is my convex mirror, then there is this magical point called the focal length, just like we had for the concave, and also true, the focal length is half the radius of curvature. And so the convex and the concave have a lot of the same properties, although as you will soon see, they are reverse of each other. And so when I go to draw this, I will still put a focal point and a center of curvature, just like I did for the other scenarios. But here is why I call this mirror the boring mirror, not the fun mirror. This is the boring mirror. And I call it the boring mirror because it only does one thing. I mean, look what happens here. You cannot get the object between the focal length and the center of curvature. That's on the other side of the mirror. That's you would be inside the mirror. You're not even using a mirror. I don't even know how to explain that. So unlike the concave one that we just did, where we had 3 scenarios and 2 different sets of equations, we don't have that. We don't have the fun ability to make things bigger and smaller, to make them real or virtual. We only have one case. And so let's draw that one case here. And so I'm hoping what you saw back here with me putting in this convex mirror, and it's spreading out from this magical point, will show up when I draw it over here. And so if I take the red marker and I draw the first ray that is heading towards the mirror, it would bounce off and go where? Well, that's why I was trying to show you this. It would come in and it would bounce off, and it would bounce off in such a way that it would appear to be coming from this magical point that we call the focal point. So if I draw a dotted line, because it doesn't really come from here, but it bounces off as if it had come from there, that will help me accurately draw where does that ray go. And by the way, I would say these rays are probably harder to draw than the concave. So even though it only does one thing, I like to do this one last. This is the one I think is harder, even though it's boring in terms of the physics of what it does. It is probably the hardest in terms of drawing the rays and getting the similar triangles. Because the other one, the second one, which in the concave, the second one was always the harder one. This is even harder still. So what's the second ray? What is the opposite of going parallel and then bouncing off? Well, it would be saying going parallel after it bounced off. Okay, so how do I draw that one? Well, just like we did in here, we would draw it as if it was coming from the focal point, or in this case, we would draw it as if it went right through the focal point and then hit the mirror. Now, in this case, the focal point is on the other side of the mirror. And so the thinking would have to be something like this. What if I drew it and it's heading towards the mirror? And if the mirror wasn't there, it would have gone through the focal point. So in other words, it has that correct angle as going to the focal point. Because that's the one I know that when it hits, it goes off parallel. And so I would say that's the reverse one. And those are the two to draw. And like I said, the second one is probably the harder one. But here's how we're going to come up with the equations. Just like before, let's see if we can figure out where the image is. So if you start here and say, well, this ray goes to your left eye and this ray goes to your right eye, and your brain were to trace them back, obviously they don't meet out here, so the image is not a real image, but they do appear to be coming from someplace behind the mirror, so it's going to be a virtual one. Clearly this ray that's parallel appears to be coming from somewhere back like this, and this one appears to be coming from somewhere back here, and then they cross right there. So there's your image. And so let me put the word image. Let me put the word virtual image. And I'll say it again, I call this the boring mirror, not because it doesn't have any usefulness to it, but it only does one thing. And it does this. It makes a virtual image, and notice this image is right side up and smaller. That's all this mirror ever does. And so you probably could see that in this shape or in this shape. It doesn't matter really which one, although this one's curved so much it might be hard to pick up on camera. But if I just held this and you took a look at the room and maybe Ron or these desks out here, right, as I look at those, you'll see that it makes everything right side up and smaller. And so hence the name boring mirror. But useful. Where do you see this? And usually when I say that in a face-to-face class, a student or two says, well, I've seen this at blind spots, like on mountain roads, or getting out of a tight driveway or a tight parking lot, or even in the hospital where you'll have these corridors, you know, because there's a lot of traffic, and so they'll mount these convex mirrors up there, so as you get there you can kind of see it's somebody coming, and all those are true. And so its really good advantage is it takes the light from a wide angle and then brings it back. And so its big advantage is it's what we call the fisheye view, right? It's got a wide angle of view. Now the fact that it makes things smaller isn't so good, because then it's hard to see details, but nonetheless it works really well for that. Now usually, again, in a face-to-face, somebody says something about the passenger mirror on their car, and that's true. I don't know if you've ever looked, but if you haven't, take a moment next time you sit down in your car and you look not at your rear view mirror, not at your driver's mirror, but the passenger mirror. You look out that mirror. There's usually writing on the bottom of it that says warning or caution, objects are closer than they appear. Because that mirror is curved a little bit. Now it's not as curved as much as this one. This one, if I just held it in front of you, you'd say, oh yeah, that's curved. But that passenger one is curved so little. It depends on what kind of car you have. Some are curved quite a bit and you can really tell they're curved. But some of them are curved so little that you don't really notice they're curved unless you look really hard at it. And if you don't notice it's curved, you may think that what you're seeing there is like a flat mirror. And that is, it's not making things smaller, but it's keeping them the same size. And so that's why they give you that warning. They say, hey, be cautious when you look in this mirror, because the reason things are closer than they appear is this mirror is also making them look smaller. So we curve the mirror for the advantage of having a bigger angle, so you don't have as big as blind spot. There still always is a little bit of a blind spot. But they make it a big angle, and that's helpful. That's why the curvature is there. But the disadvantage of that is now things look smaller. And if they look smaller, you might interpret it as being further away than it really is. And so that's the warning in there that says, hey, objects are closer than they appear. And so be careful when you look in that mirror. And you know, there's another fun place that many people don't even know. And the equipment I have doesn't illustrate it quite well, because my mirrors are part of a sphere. In other words, I would say they are curved left and right, and they are curved up and down. But what if I had something that was curved more like this, a cylinder? So it was curved left and right, but not up and down. Because if you put something in front of it, up and down would be like a flat mirror. So you wouldn't change the height up and down. But left and right, it would look smaller. And so, ladies, if you're trying on clothes in a fancy dressing store, they love to put these type of mirrors in the dressing rooms. Because when you stand in front of it, you will see your same height. But with a small curvature, you will look 5 to 10 pounds smaller and lighter. And so that's the whole idea, is to get you to buy that outfit. And they curve that mirror a little bit better. That's why Consumer Magazine always says, you know, your best bet is to bring a friend with you if you want an honest opinion. You know, how do I look in this outfit? Or take a picture of yourself, which is kind of hard to do, but nonetheless, that's kind of what they say. But you can get some disinformation from their fancy mirrors. Their fancy mirrors are there to sell you merchandise. And so that's why they put them in there. Well, let me keep going here with the equation, because like I said, this has taken me a long time and longer than I really planned. But I think it's important to go through this geometry, because like I said, in the past, I've left students to say, oh yeah, just do the geometry, and it's been hard for them. So one more set of geometry here. Let me grab my markers. I'll grab the blue one again, blue marker right here. And if you remember, the blue triangles I've been making have been one that involved the object and the image projected into the mirror. All right, so why don't I do this? Here is the image. Why don't I just kind of say, well, the height of the image would be right there. And the height of the object would actually be right there. And so I could even put here height of image, and maybe I'll put it here also. This really is the image, height of image. But you can see that I can make myself a set of overlapping blue triangles. Here's the small blue triangle, and then here is the big blue triangle. And if we use the same symbolism, this is the distance of the object This then is the focal length. You can see here that this small blue triangle, if I write out the ratio, I would have height of the image is to the height of the object. So this is to this. As this distance, which is the focal length, is to this whole distance, which is object distance plus focal length. And so again, you'll see that that equation is different from this one and differs from this one. Each of those, although they switched, each of those at least had a minus sign. This one over here has a plus sign. And of course, with the plus sign, you can actually see then that this ratio right here is always less than 1. And so that's why I was saying this will always give you an image height that is less than 1. And so your image will always be smaller than your object to get this ratio less than 1. And then the other set of triangles, the green one, would be the same set I've been doing, which would involve the projection of the object into the mirror together with the actual image. Oops, dropped my marker. And so I would have something that looks like this. And so I would have a small green triangle inside of a big green triangle. And the small green one would be right here, so it would be the height of the image is to the height of the object. So height of the image is to the height of the object as, and this one might be a little bit hard to see here. This would be then right here would be image distance. And so this small little piece right there would be focal length minus image distance. And that's what I'm looking for. So I'll say it again here. Height of the image is to the height of the object as this distance, which is focal length minus image distance, over this whole length, which is focal length. And so just like those other ones, I would do this calculation first, which would give me the height of the image. Once I have the height of the image, I could come down here and do a calculation of where is the location of the image. And so again, you can see this equation is a little bit different than this one. And so let me put a box around this one and say this would be true for the convex mirror. And here's some great news here. Is there's no bunch of equations I can do with this one. This is all I can do with that one. So I don't have to say where and put a limitation on where the object is. And so now I have all three scenarios. This is the scenario and the equations I would use if the object distance is greater than the focal length. And this scenario would give me a real image. Now, the picture I still have up here would give me a real image that is bigger than my object. But if the object had been out here, then I would get an image that is smaller. So this kind of represents two scenarios. And then, of course, this is the next scenario where you can get an image that is bigger and right side up. And here you can get an image that is smaller and right side up. And so we've got all four combinations. We can get bigger upside down, we can get smaller upside down, we can get bigger right side up, and we can get smaller right side up. And so those are our four combinations, and depending on what we want to do as an optical engineer, we would use the different mirrors to do different things. And of course now it can get real exciting, and we're not going to go that far, but what happens if you put two mirrors back to back, or then even some lenses, and that's the next chapter. Well, I better wrap up this chapter and then get us into and finish up 18 here. But I'm going to go ahead and just say there are two last things, two and small things that your author does before we leave here. And the first one is then, what is the speed of this light? And that's going to lead into the beginning of the next chapter, because we're going to say the speed of light, but we're going to say a speed of light in a vacuum. In other words, if there are no other molecules around, because as we get started into chapter 18, we'll see that the speed of light is affected by those molecules, and it drops a little bit. But the speed of light in a vacuum is roughly 3.00 times 10 to the 8th meters per second. I think a little more accurate is, 299,000 458 meters per second. I better double check that. I don't know if I have that well committed to memory. Yeah, that's it. And so that's the speed of light. It's really, really fast. To emphasize that it's really, really fast, maybe it's kind of nice sometimes to put it in miles per second. It's 186,000 miles in 1 second. That is really, really fast. Or maybe another one. It's 7.5 times around the world in 1 second. And so these fiber optics are really great that we've got a line all over the oceans of the world, because that means I can get my information. I don't even think about how far away it is. I mean, nobody sits down in front of a computer and clicks on a link and says, oh, I wonder if this link is in Australia versus the next city over. Because you don't go, well, it's in Australia, you know, that's going to take like 10 minutes for all that information to get here. No, it doesn't. The time it takes for it to go all the way from Australia is really kind of irrelevant compared to the other things going on. And so whether you're getting information from just the next city, or even in the city, or even from your friend who's just in the computer next door versus Australia, you don't think much about it. And that's because these pulses of light are traveling around in these fiber optics. And they could, you know, in a fraction of a second go all the way around the world. And so we don't think about that being our limitation on how quickly we get our information. So that's one of the two things. The other big one here, and I'm hoping you can see this on camera, goes back to our colors when we started this chapter. I said that, you know, if I picked up these laser beams here, and so I had this one here which was green, and maybe I'll clear off the board here a little bit, and I shine it on here, and I've got this green. Why is it green as opposed to the other two I showed you, which were red and violet? And I think I still have the violet one here. I don't know where I did with my red one here. Here's the violet one. But I was saying here that just like the different tones you hear in sound waves, your eyes can detect the different frequencies, at least up to a limit. And so what we call the visible spectrum, your eyes break apart and say for the low frequencies, your brain calls red. A little bit higher in frequency, your brain calls orange. A little bit higher, your brain calls yellow. A little bit higher, your brain calls green. A little higher, blue. A little higher and less of a common word is indigo. And then a little bit higher, and the highest your eyes can see, and so I will say the high frequency, is then in violet. And so just like we did for the sound waves where we had a sonic range, we could have then a visible range, and we could have then frequencies lower than that. So we would call these infrared. Now you couldn't see those with your eyes, just like you can't hear infrasonic. And then likewise, at these high frequencies, you could have things higher in frequency than violet, so we would call it ultraviolet. Then again, we've got a lot of ultraviolet from our sun coming into the atmosphere. So you walk outside. When you walk outside, there's a lot of infrared. Those are the kind of stuff you feel, and you don't necessarily feel the visible light, although that has some energy, but it's a lot of the infrared. In fact, today's weather with our June gloom, this is about perfect because the light gets scattered and you don't really actually see the sun, but it's thin enough right now that if you walk out there, you can feel that warmth, and you can go, okay, I can tell the sun is over here. I can feel that warmth. So I don't see it, but I feel the infrared. Now, of course, once the June gloom burns off, then it looks very, I'll say, colorful, because when all of these colors are going to your eye at the same time, your brain calls it white light. And so the sun gives off all these frequencies. And so you walk out into the sun, you will, there'll be green light coming from the sun, but there'll also be plenty of yellow and oranges and reds and blues and indigos and violets. And so when you get all of that, your brain calls it white light. In fact, that kind of reminds me, indigo, as I said, wasn't a very common word, but maybe the best way to call this is blue. What a scientist would call blue, most artists would call a light blue or a baby blue. And what a scientist would call indigo, an artist would call a royal blue. Or you sports lover would call a Dodger blue. And so this is kind of so the royal blue and the sky blue or the light blue. And then the violet, I think the other ones I think are common enough that you know. But anyways, when all of them mix together, you get white. And so I thought I would finish then the chapter here and say, well, why don't I turn on a standard incandescent light bulb? And so there it is, white. I'll turn off the rest of the lights in the room. And we would call this white because what's coming from it are all the colors. But Ron has, and go ahead and put a little machine that he can put in front of your camera lens there. And so I'll give him a chance to kind of get that straightened out. But once he gets that in front of there correctly, it should then separate out, and you should see the whole rainbow. And that's what I wanted you to see, the whole rainbow. The red, the orange, the yellow, the green, the blue, the indigo, and the violet. So were you able to get it aligned, Ron? Yeah? Good. Good, good. Because then one last thing, and I'll put closure to this. A good way to memorize this then, I don't know if you saw me when I wrote it, but it can be easily memorized as a name. And so if it's Roy G. Biv. And so we like to just say, hey, the spectrum is a famous person called Roy G. Biv. And so it's a good name and an acronym to try to remember what are the colors of the rainbow. And that's what a rainbow is doing. And we're going to talk about that in the next chapter. A rainbow then separates out the white light so you can see the individual colors. Well, I better get started to the next chapter. How have we been doing on time? I know we had that power outage.